Hello everyone. Today we are going to discuss here the mutual inductance. Actually we are going to find an expression for mutual inductance between two coils, or we can say it to be two solenoids, coaxial solenoids having length L. So let us see how the expression can be calculated. Here we can see in the diagram there are two solenoids having same length L. The first one, that is S1, having a radius r and an area which can be given by pi r square, and another solenoid S2 which is coiled over S1 having the same axis but the radius is more. Now what we are going to consider, first we are going to consider that current I1 flows through S1 and which changes, because of which induced EMF is produced in S2. And in the second case we will consider current I2 to be flowing through S2 and which changes, because of which induced EMF is produced in S1. And in both the cases we are going to calculate the value of mutual inductance. Okay, and first we are going to consider here that the current I1 is flowing through S1. So first of all, let us find the flux linked with S2. The flux linked with S2, let it be given by phi 2, will be M21 into I1. F2 is this is the flux linked with S2 due to the current I1 which flows through S1. Okay, so this is the value of flux. We have actually discussed this formula. Flux is given by mutual inductance into I. The value of M12, it is written M21, sorry, it is written M21 because you can see here mutual inductance of the coil when induced EMF is produced in the coil 2. That's why 2 is coming here. Mutual inductance of the coil, or between the two coils, when their induced EMF is produced in coil 2 due to change in current in coil 1. Okay. So that's why M21. The current is there in the first coil S1, so it is I1 is the current, and the flux linked we are considering it to be in the second coil S2. So that's why it is given by phi 2. Now there is another way of calculating the value of flux. The value of flux phi 2, which is linked with the second coil, can also be given by the general formula for flux linked is given by B dot A. Now this is the flux linked with the second coil. So magnetic field in the second coil will be due to the current in the first coil, and the magnetic field is actually produced in the first coil. So it is B1. And the area of S2 is to be considered here, but the whole cross-sectional area, there is no magnetic field. Magnetic field is present only in the cross-sectional area A, which is of the inner coil, because the current is flowing through the inner coil, so the area will be A only. We will not consider the area of the second coil, only the area of the first coil will be considered, because the magnetic field is already present there only. So this B1 dot A will give the value of the magnetic flux linked with one turn of the coil S2. So N2 is the number of turns per unit length of the coil S2. So, and the length is L, so the total number of turns will be N2 into L. So this will be the value of the flux linked with the coil 2. So we can write here, now B1 and A, the cross-sectional area, the area vector and the magnetic field, obviously they will have the same direction. So here it is B1 A cos 0, which is 1, and into N2 into L. Now the value of B1 for a solenoid, when current I1 is flowing through it, so it is mu naught Ni, so it is mu naught N1 I1. This is the value of B1 into the area A into N2 L. So therefore, finally the value of phi can be written as, phi 2 can be written as, we can write here as mu naught N1 N2 I1 A L. Now you can see we have two values of phi 2. One we have considered earlier in terms of the mutual inductance, and secondly we have considered in terms of magnetic field and the cross-sectional area. So these two terms represent the same thing. So therefore, comparing these two things, we can therefore write M21 I1 will be equal to mu naught N1 N2 I1 AL. So obviously this term I1 and I1 cancels out, and so we have the final value M21 can be written as mu naught N1 N2 AL. So this is what we are getting for the mutual inductance when we have considered the current is changing in the first coil S1 and the magnetic flux is linked, that is the induced EMF is produced in the second coil. Now let us consider the second condition, in which we are going to consider a current which flows through S2 given by I2. Now there is no current in this first coil. So there is no current here in the first coil, but the current is there in the second coil S2, which is given by I2. So we are going to calculate the flux linked with the first coil. So it will be M12 into current, which is I2. This is the flux linked with S1 due to the current I2 in S2. Okay, I hope you understand this. Now also we again the same way we will calculate the value of phi 1 as B dot A. Now this time it is B2 because magnetic field is due to the second coil. Dot area remains the same. You need to understand this very important concept here. See, now we are considering that the flux linked with the first coil. Now already the area is A. B2 is present within S2, which has the spread more than the area A. But we need only up to the area A, which is the common area. So that's why the value of area still remains the same. And this is the flux linked with one turn of the coil S1. So total number of turns is N1 into L. So therefore we have the value here for B2A into N1L. Angle theta is 0 between B2 and A. The value of B2 is mu naught N2 I2 into A N1L. So finally we have phi 1 is equal to mu naught N1 N2 I2 AL. So we have a relation here for phi 1, the flux linked with the coil S1, and we have a relation here also. So when we compare them, so if you see here, if we compare them, then I2 terms cancel out and the value of M12 will be given by mu naught N1 N2 AL. AL. You can see and you can compare the two values. M21 and M12. M21 was the condition when the induced EMF was produced in the second coil S2 due to the change in current in the first coil S1. Whereas M12 is the condition mutual inductance when the induced EMF is produced in the first coil S1 due to the change in current in the second coil S2. But both the values are same. So what we can write here, the general equation which we can write here, M, which is equal, both the mutual inductance is equal. So whether we take the current in any one of the coil, the induced EMF is produced in the other coil and the mutual inductance remains same. This is known as reciprocity theorem. That is, it doesn't matter in which we are considering the current. Okay, so reciprocity theorem, and the value of mutual inductance is given by mu naught N1 N2 AL. It can also be written as, see, mu naught into N1 and N2, number of turns per unit length. Now, if the total number of turns in the first coil be given by N1 and total number of turns in the second coil given by N2, so small n1, number of turns per unit length, will be given by N1 by L and N2 will be given by capital N2 by L. So L square will be there, that will cancel out with the L here. So here only A will be left out. Or we can also write here like mu naught N1 N2. The value of A is pi r square, so we can write in terms of radius also. So all these values actually represent the formula for mutual inductance. So we have a relation for mutual inductance here. You can see here. This is mutual inductance between two solenoids. So I hope this is very clear to you. Now let us quickly discuss the factors on which it depends. Yes. See the factors on which it depends. We have the equation which is given by mu naught N1 N2 AL, or it can be given by mu naught N1 N2 AL by L. So it depends, like capital N1 or small n1, the values are you know. So the factors on which the value of M depends, mutual inductance depends. The first is, we can consider the number of turns. You can see here the number of turns, N1 and N2. So mutual inductance is directly proportional to the product here. Okay, so more is the number of turns, more will be the value of mutual inductance. It depends on the cross-sectional area, which is the common cross-sectional area. Okay, so M is directly proportional to A, or we can write M is equal to, is proportional to pi r square. Okay, then it also depends on the permeability of the core material. See, whatever is taken in the core, the permeability, if it is air, then the permeability is mu naught. But if it is not air, instead of air, some other medium is there, then mu will be used, or you can write it as mu naught into mu r. So it depends on the permeability of the core material. It depends on the fourth point, it depends on the relative separation. That is, it depends, like when the separation between the two coils is more, then the mutual inductance will be less, inversely proportional, and it depends on the relative orientation. The examples are given here, A and B. You can see here, orientation, when both the coils are taken to be coaxial, then whatever flux linked with the second coil will be the same in the first coil. So you can consider it to be the mutual induction to be the maximum. But in the second case, B, you can see that they are kept perpendicular to each other, where the magnetic field is minimum. So I hope this is clear to you.